All right, everybody. Today we are going to talk about the normal distribution of data. A quick reminder about what the distribution of data kind of looks like. It's either asymmetrical, which in other words is unsymmetrical, or it's symmetrical. The three patterns to the left, skewed right, or no pattern, are obviously asymmetrical data distributions. The normal distribution is symmetrical. It has a bell-shaped curve, and that's really what we're going to hammer down today. The normal curve, it is the bell-shaped curve. I'm sure you have seen this a lot about scores of the SAT or the IQ score. There's a lot of applications for the normal curve. Okay, so we need to kind of be familiar with different types of statistics. The main important ones you need to know for the normal curve are mean, which is the mu Greek symbol, which is the population mean. Standard deviation is the sigma Greek letter. Because this is a normal curve, our mean or mu is always in the center of our distribution. So that's that middle line right there. Then to go to the right, we just add the standard deviation to our mean. That is one standard deviation above the mean. Two standard deviations above the mean is you just add the standard deviation twice to our mean. Then three standard deviations above the mean is far to the right. Then to the left, one standard deviation below the mean is represented by subtracting the standard deviation from the mean. Then two standard deviations away from the mean, you subtract the standard deviation twice from the mean, and then you subtract it 3 times from the mean. The empirical rule. This applies to the standard normal distribution of data. And this is going to be very, very handy for you. So if you want to, I highly suggest this, writing it down, because you're going to need this going forward. So the total area underneath our bell-shaped curve, if we were to add it up as a decimal, it would be 1. Or it would be 100%. So let's break this down a little bit. So one standard deviation above and below the mean accounts for 68% of the entire area underneath the bell-shaped curve. Two standard deviations above and below the mean account for 95% of the total area under the bell-shaped curve. So almost the entire area underneath our bell-shaped curve is 2 standard deviations away from the mean. Then 3 standard deviations away from the mean is 99.7% of our entire data. Okay, so the probability that something is going to occur 3 standard deviations above or below the mean are 99.7%. So almost 100% probability that something would happen. Okay, so to break this down further, this will make a little bit more sense whenever we start to see some examples, but the distance underneath our bell-shaped curve from the standard deviation in the middle to 1 standard deviation above the mean is 34%. Likewise, if we subtract 1 standard deviation from the mean, it's also 34%. If you add those together, you get 68%. To go further out, the distance from 1 standard deviation above the mean to 2 standard deviations above the mean, as well as below, is 13.5%. Then we're going to get smaller. So the distance between 2 standard deviations above the mean and 3 standard deviations above the mean is 2.14. Same thing with the distance between 2 standard deviations below and 3 standard deviations below the mean are 2.14. That basically means it's a very rare occurrence. okay, of something that's going to happen. Somebody scoring really, 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 really high on an IQ test, right? 2.14. Okay. Then from 3 standard deviations above or below the mean and beyond is not even a full percent, not even a 0.5%. It's very, very rare, 0.14%. In other words, if you were to add up all these percentages that we have listed out underneath our curve, it should add up to about 100%. Okay? So let's put this to work. Example number 1, assume the heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. The important information in our example is the mean and the standard deviation. So mu is 63.6 and the standard deviation is 2.5. I have my bell-shaped curve here because it is normally distributed. So I'm just going to fill in all the information that I know. I know that the mean goes in the very center, 63.6. To find one standard deviation above the mean, I'm going to add 2.5 to 63.6, and I'll get 66.1. And then I'm just going to keep adding 2.5 to get to the next standard deviation above the mean. To calculate one standard deviation below the mean, I subtract 2.5 from my mean, 63.6, and I get 61.1. To find 2 standard deviations below the mean, I subtract 2.5 from 61.1, and I get 58.6. And then subtract 2.5 again, and I get 56.1. So this is part A of example 1. I have labeled all of the parts of my normal distribution. Letter B. What percent of women are between 61.1 inches and 66.1 inches? I have all the information that I need already laid out on my normal curve. So the first thing I do, I identify 61.1 and 66.1 on my number line here. I've outlined these in orange, so it's pretty easy for us to see what area we're trying to look for. So it's 1 standard deviation above and below the mean. If you are looking back at your notes, according to the empirical rule, it's about 68% of women are between 1 standard deviation above and 1 standard deviation below. In other words, if we're trying to find the area underneath our bell-shaped curve, 1 standard deviation above and 1 standard deviation below, it's 34% plus 34%, which is 68%. Letter C. What percent of women are between 58.6 inches and 68.6 inches? So just like the problem previous, we're going to identify our parameters. 58.6 and 68.6. So the distance I'm trying to find is 2 standard deviations above the mean as well as below the mean. According to the empirical rule, that's about 95% of our data. There's 95% of women are between 58.6 inches and 68.6 inches. If that number didn't automatically click to you, I went ahead and put the percentages underneath our bell-shaped curve. You can add all of those up together and you get 95%. What percent of women are between 61.1 inches and 71.1 inches? First thing I do, I put a box around 61.1 inches. That happens to be 1 standard deviation below the mean. But 71.1 inches, it lands between 2 and 3 standard deviations above the mean. So we're going to approximate. That's 1 standard deviation below and about 3 standard deviations above the mean. So if we add all of these percentages up, according to the empirical rule, it's going to be approximately 83.64%. So for the time being, we're just going to approximate. E. What percent of women are less than 63.6 inches tall? 63.6 inches tall happens to be our mean. And every height below our mean basically just means that we are splitting our bell curve in half. So instead of adding all of these up or trying to memorize that 3 standard deviations below the mean is about 50%, just remember that if we're talking about in terms of mean and it says what percent is larger or less than the mean, it's just 50% of the bell-shaped curve. We're just cutting our bell-shaped curve in half. 3 standard deviations below the mean is 50%. Example number 2. According to the College Board, Georgia seniors graduating in 2008 had a mean math SAT score of 493 with a standard deviation of 108. Assuming the distribution of these scores is normal, find the following. So the instructions are for us to fill in this bell-shaped curve. If you would like, go ahead, put me on pause and find out the answer for yourself. I'll let you guys take a second. All right, welcome back. If you went ahead and filled in this bell-shaped curve, go ahead and check your answers along with me. So the mean, or mu, is 493. The standard deviation is 108. So the mean, which is our middle number, is 493. Then I just add 108 every single time to get my next standard deviation. So one standard deviation above the mean is I just add 493 plus 601, 493 plus 108, and I get 601, 709, and then 817. Then on the left side of my bell curve, subtracting the standard deviation, I get 385, 277, and 169. What percent of Georgia seniors scored between 277 and 601? So this is just like what we've been doing. We first identify our parameters, 277 and 601. I want to know what's the area underneath the bell-shaped curve from 277 to 601. That's 2 standard deviations below the mean and 1 above. If we are going by the empirical rule, which I totally think you should, we're going to get 81%. If there were 50,000 graduating seniors in 2008, how many scored between 385 and 709? So this is kind of a 2-step question. First, we have to find the percentage of students who scored between 385 and 709. So we identify 385 and 709 on our bell-shaped curve. That happens to be 2 standard deviations above and 1 below the mean. So if we add up all of the percentages underneath our bell-shaped curve, that's about 81.5% of the population. Then we have to find what is 81.5% of 50,000. So you translate 81.5% to a decimal, and then you multiply that by 50,000. And you get 40,750 students. And these are just the percentages of each section of the bell-shaped curve. Again, that's how I got my 81.5. What is the probability that a student would score above 709? So looking on my bell-shaped curve, I identify 709, and that's far to the right of my bell-shaped curve. So if I'm just looking at this bell-shaped curve, And I have absolutely no idea about the empirical rule. I don't know anything besides that I want to know what the probability of a student scoring very high is. Just by looking at the shape here, it's very small. So that tells me that my percentage or my probability has got to be very small. This is 2 standard deviations above the mean. Okay. According to the empirical rule, it's about 2.28%. The area from 2 standard deviations above the mean and beyond is 2.14 plus 0.14, which is roughly 2.28%. So it's a very small percentage of students, a very small probability that a student would score above 709. All right, example number 3. Scientists are studying the differences between crocodiles and alligators. The length of 6 crocodiles are recorded in feet. The results are shown below. Find the mean and standard deviation of the data. I've included this link here to Desmos, so if you would like to hit pause and go to the Desmos calculator, input the data, and find the mean and standard deviation, or you can use your calculator, it doesn't really matter. You can hit pause and check to see if your work is correct. All right. The mean is 19.68. The standard deviation is 2.11. So we are assuming that the data is normally distributed. Sketch the normal curve that represents the situation. This is exactly what we've been doing all along. Okay, this question is pretty easy. So if you want to hit pause and then fill this out on your own, you go for it. If you don't, if you want to follow along with me, that's cool too. So the mean goes in the middle. Our middle line is 19.68. Then we just add 2.11 every time to get our next standard deviation. 3 standard deviations above the mean is 26.01. Then we subtract 2.11 every single time. So 1 standard deviation below the mean is 17.57. 2 standard deviations below the mean is 15.46. And then 3 standard deviations below the mean is 13.35. So if you had done this on your own, hopefully you got all of those answers correct. Alrighty, so I want you guys to practice the rest of the problems on the worksheet. Alright, if you have questions, reach out to your teacher. We hope you all are doing well and hope to talk to you soon.